Okay, so picking up from where we stopped yesterday, so was discussing the codes for the non-coherent adversarial channel. I mentioned that we can use lifted MRD codes to build good subspace codes for that problem, and that those lifted MRD codes are asymptotically optimal. Okay, so they're almost optimal codes for that problem. So I think it's worth learning about how this MRD codes are constructed. Okay. So let's review this the matrix. So we need to construct matrix codes, right, for the rank matrix. That was our original problem. And you may think that it's a bit hard to construct matrix codes. So what we're going to do here, we construct from block codes. Okay? So this is a construction by Del Sartre and Danilo and others. And it's a very, very interesting construction. So basically, we recall that an extension field of Fq, so Fq to the n, can be seen as a vector space over Fq, m-dimensional vector space. So let's just find this vector space isomorphism, and then we can so then we can think of unfolding an extension field element to a vector, a row vector. We can extend this mapping to vectors over Fq to the n, so that they map to a matrix, an n by n matrix. So what we do, we just take this is a vector over the extension field. Essentially, we transpose the vector and then apply the mapping so that we get an n by m matrix. In this way, we can construct matrix codes from block codes. And in particular, we can define the rank distance for vectors over the extension field just by the rank distance between the corresponding matrix. So then a Gabby-Doolin code is simply a block code of dimension k and length n over the extension field, specified by this parity check matrix here. So it's very similar to the parity check matrix of generalized grid solving codes, except that here we do q power. So we raise to the power of q to the power of I, each entry in a column. Right? And these elements h1 to hn must be linearly independent over Fq. The assumption here. If you do this, then this block code can be shown to be an MRD code. So it has maximum possible rank distance, and the rank distance is given by n minus k plus 1. So it's very similar to MDS code. Actually, they are MDS codes as block codes with that same Hamming distance.
What is H matrix?
Right. Parity check matrix.
How do you say that they are MDS as well?
You can show that the rank distance is related to the Hamming distance, so then you can show that they're also MDS. This is an interesting observation that these codes can also be constructed from linearized polynomials. So a linearized polynomial is simply a polynomial, but only in terms that have powers of q. And linearized polynomials form a non-commutative ring under the composition of polynomials. And then you can there's another possible construction for Gabby-Doolin codes as the evaluation of the polynomial on n linearly independent elements. Interesting to observe. So I won't discuss here encoding and decoding algorithms for Gabby-Dooley codes. So they are very interesting decoding algorithms, very similar to the decoding algorithms for Ritz-Solomon codes. I just want to mention that these algorithms use linearized polynomials, and very often you see operations with this Q exponentiation. And this may be not very simple to implement in practice, but if we use a normal basis for the extension field, so to implement operations over the extension field using a normal basis, then Q exponentiation simply becomes a cyclic shift, and then this exponentiation becomes easy to compute. Okay, multiplication becomes more complicated if you use a normal basis, but then you can use optimal or low complexity normal basis, and then you can get the same order of complexity as using a polynomial basis. And you can also make this algorithm even more efficient if you use a code that is somehow matched to the normal basis, so that those h's are these Q powers of your normal element. These codes have also been called cyclic Gabby-Dooley codes because they close to cyclic shifts. And then we can show very fast algorithms for encoding and decoding this code. Okay, so essentially we are harnessing the power of block codes to construct this matrix codes. Another useful observation here that comes from the result that MRD codes are optimal for the coherent rank erasure channel is that these codes can correct, so they're able to correct rank deficiency. So if you're able to communicate under matrix multiplication with a matrix that is rank efficient. So if you just take, so suppose you take a Gabby-Dooley code, or an MRD code in general, with rate k over n. So this you can imagine this as if you have k information packets and then you code with n minus k parity packets. So parity package. If you then transmit this as a matrix X and observe a matrix Y that is A times X and A has rank at least K, that's all you need, then you can uniquely determine the original matrix X. Okay? So A could be just a K by N full rank matrix, and then you can decode it. So this property is very useful and has been used in many applications of MRD codes. So I'll just mention some of them. One is to achieve perfect secrecy against an eavesdropper in a network using network coding. So it's probably not easy to see how this would, how would you get this secrecy from this property, but it's possible. So essentially, the proof of secrecy involves a rank erasure channel. So the property of MRD codes comes handy in that problem. It can also be used to control the failure probability of random network coding. So rather than going to a higher field, using a field of high cardinality to reduce the probability of a dependent packet, receiving a dependent packet, you can even use key equal to 2, but then pre-code your data with the Gabby-Dooley code, an MRD code, and then you can easily control that failure probability and make it as small as you wish. So if you're interested in this, you can go to the poster of my student Ricardo. And it has also been used to build optimal locally repairable codes for distributed storage systems. That's a more recent application of this. MRD codes. Okay, so this is just to finish what we were discussing yesterday. So there are many other topics that I didn't discuss. I can tell you about if you're interested. So encoding and decoding algorithms, interleaved capability codes, very interesting family of MRD codes. You can do list decoding. There are ways to do error control with multiple sources, perfect secrecy, again from the dropper. You can try to combine secrecy and error correction. That's another application. And there's also a whole area of studying random matrix channels, right? Because here we consider an adversary, but we could also consider errors that are random, and then we can study what's the capacity of those random matrix channels. Okay, we can also use even MRD codes for that problem. Okay, so any questions about that before we move on to the second part? So now we've been talking about algebraic codes, extension fields, right? So now we're going to completely change topic and talk about vectors over complex fields. Right? So you have to switch in your brain from extension fields to complex numbers and signals and vectors. So let's recap the use of net coding for this two-way relay channel, right? So we have seen this picture before. If we use just routing, we can these two nodes can exchange packets in 4 time slots. Remember that. With net coding, we can do a little bit better. We can do it in 3 time slots by having this relay computers export and broadcast the packet to the 2 nodes. But what about we do it in 2 time slots? Okay, so how can we do that? So we just send the two nodes send their information, their signals at the same time. The signals will interfere on this relay. So relay, I'm just making this illustration here. The relay is receiving somehow the sum of the signals, right? And then it can just infer the XOR of the 2 packets from the interference that it has received, right? And then it can just broadcast that XOR packets with both nodes 1 and 2. Right? And then you can do it in 2 time slots. It's easier said than done. So the crucial problem is how do we do this? And that's what we're gonna talk about now. So this is physical layer network code. So let me make a basic problem formulation. Later on we will extend this problem formulation. Suppose we have a finite set here called the message space. So this is the set from which we will take our messages. This could be the set of vectors of length k over f2. And each user has a message from that set, and it will encode into a vector x index L, which is a complex n-dimensional vector, and then transmit that over the channel. So then the relay will receive this the summation, right? Scale summation of these vectors plus noise. So that's the vector z. So this the sum of vectors is scaled by some fading coefficients h1 and h2, and z is what also noise vector. Okay? And then the problem is, so this is a summation over complex numbers, right? And the problem is, how do we extract a linear combination of messages that are, of course, over this message space, which is finite. So the finite, linear combination over finite structures. For instance, vector space could be over F2, and that we're trying to extract from a linear combination over complex numbers. So how do we do that? That's the problem, okay, that we're gonna address now. Before I move on, let me just do like Danilo and ask you a few questions to the electrical engineers among you. So first of all, why? So he mentioned that why this vector z is assumed Gaussian, right? So that's because of thermal noise at the receiver. Fading coefficients, I think this is natural to understand. But why complex? Why are we using complex vectors? Yes, so, and why vectors? So let me do one step back. Why vectors? Why do we have vectors? Aren't we transmitting signals? Waveforms? Why do we talk about vectors?
I and Q.
Sorry?
I and Q.
I and Q, can you elaborate a bit more?
Imaginary part, big part, signals after going to basement.
Going to baseband, so that's the baseband equivalent model of a single carrier modulation, right? After magic filtering and sampling, so then we get a vector model. And why complex? So we're representing the magnitude and phase of the sinusoids that we're sending over a symbol interval. That's why. Sorry? Vectors, because there's a model after sampling. Right? We send waveforms, but at the receiver we sample them to get vectors. And essentially there's a vector space isomorphism between the set of all possible transmitted signals and vectors over the complex n space. Okay, so here the complex numbers are useful because we're transmitting waveforms that have magnitude and phase. But again, another question. So why do we very often see models over the real vectors? Why not complex? Especially when we're talking about a point-to-point channel. Why do we see vectors over the reals? Especially when you know the fading coefficients at the receiver. Anyone like that? Right, we very often see vectors, like the channel model with vectors over the reals. And then, but now we remember that they're actually complex. So why use reals? Why is this very common? Sorry? Yeah, so these are just two orthogonal dimensions, right? But how can you transform them into real vectors? So this fading coefficient could be a complex number.
You would prefer to work with C rather than with U5?
Yeah, it's easier, right, to work over the reals. So that's a starting point. So, but probably another important reason is that for a point-to-point channel, so you have just a single transmitter, if you know the fading coefficient here, it may be complex, right? But you can just compensate the phase, right? So just compensate and make this coefficient a real. And then if you have a real multiplying the real and imaginary parts, then you can just extract the two of them and treat as independent channels. You can even put make a longer vector, vector of length 2n, right? And then since the noise is circularly symmetric, then it doesn't change the statistics. Right? So then you can do simply with a real vector. However, in our problem we have more than one transmitter. So even if we compensate the phase for one, we cannot do for the other one. So we really do need to work with complex vectors. Okay? Yes.
One other engineering question. You said that in the relay we get somehow the summation of the signals that transmitted or transmitted, right?
Sure.
So is there any discrepancy with the conservation of energy? Because we know that the energy is proportional to the square of those amplitude of those signals, right?
So this is a linear model. You need to use a linear modulation in the add. So you need the signals to add as complex numbers.
Okay. For instance, if you use 4 PSK equals transmitters and one and the other sends I, what we are going to receive is going to be I plus 1.
If the fading is 1, fading, yeah, sure.
But in that case, you know, the power of I plus 1 is
You'll be receiving higher power. That's true.
higher than the summation of the power of the transmitters.
Yeah, it depends on how they align, right? So typically it would be the summation of the powers. We can discuss more about that later on. Yes.
Why are we trying to compute the sums of the messages and not the sums of, say, A1 x1 plus A2 x2? Why W1 plus W2?
Why do we consider it to be A here?
No, why W1 instead of x1? Why are we trying to, why is the way to estimate sums of messages rather than sums of, say, whatever is in some linear combinations of some predetermined coefficients?
So why do we want a linear combination over this finite set rather than x1 and x2?
Over the
right?
coded thing. Because you get, essentially you're getting a linear combination of x1, x2 plus z. So you need to better estimate a1, x1 plus a2, x2 to some other a, so you can take it down to something close. But you here you're doing even w1 to a. So you're somehow on the right, under the coding schemes of linear or something, you made up this seems to be more than what you want.
Bit more than what we want. Why? Actually, the reason we want something over this finite set is that then we can use, let's say, the same constellation for
Yes, but-
relaying here, right?
But it's not
That's
necessary.
all we need.
It's not necessary, because you could transmit a different constellation.
But then you're expanding, right? What you
You're using two different codes.
Yeah.
Because it's more natural, it seems, to estimate. You're getting a linear combination of the transmitted symbols. So you want to estimate something that's also a linear combination of the true signal that you transmitted. You want to put noise. But here you're trying to transmit the same message. It seems to be a bit more ambitious to.
So do you agree that it's actually not more ambitious? So suppose you have this linear combination of the signals, so you somehow you were suggesting just try to get rid of the noise, right?
Not H1. H1 may be too continuous. So you want to quantize H1 to some constellations and then estimate the nearest constellation.
Yeah, you are quantizing, you are compressing in some way, right?
Yes.
But then all that we need to solve this problem here, right, is to send a linear combination of messages. We don't need more information than that. Right? So even if you find some linear combination of the vectors here, you could then map to a linear combination of messages.
That's only if the coding scheme is linear. That's
Oh, if the coding scheme is linear, we will assume such linearity here.
yes.
In the
Then
coding
it's
scheme.
let's equal it. Then it's kind of equal. But if it's not, then you may lose something.
That's right. So if the coding scheme is non-linear, then
It's better to just do it in forward.
yeah, yeah. What happens is that this is already very good. So we see some results that are very motivating when we use linear codes, and also, yeah, I think there are results for such good results as we see for non-linear codes. I'm not aware of that. So this is something that works.
I'm not saying
Yeah, it could be something to study, but I bet it's going to be much harder. And also harder to implement. So linearity is somehow useful for us, right? We've been discussing about linear network coding, so we were trying to compute linear combinations. That's just the problem we're posing. So suppose you want to do that, you want to compute that linear combination of messages, but you're looking at a complex vector that has interference of the vectors transmitted. So how do we do that? One approach is to do decode and forward. So just do what Nina was discussing yesterday. So treat this as a multiple access channel, and then you can encode the messages in such a way that the relay can decode them individually. So first decode one, and then subtract and decode the other, or something like that. But in the end, it will get both messages, W1 and W2. Once you have both messages, you can compute whatever linear combination you want. So this is a possible solution, but intuitively we could do better, right? It is intuitive that we should be able to do better because we're not interested in the whole pair, but just a function of two messages. So it's less data we're interested in. So how can we do that without first decoding the whole pair of messages? So let me show you a very simple example, very real world, very down to the earth example. So this is the uncoded BPSK modulation. So we're just suppose so we're just using one symbol. Okay, our vector is actually just one symbol. The messages we want to transmit are just one bit. So suppose the constellation for each transmitter is this one. So to send a bit 0, you send a symbol -1. To send a bit 1, you send a symbol +1. What happens is that, and suppose that the channel coefficients are just 1. So just have addition +1. What we'll see at the relay is this constellation here, where we have ambiguity in case we receive this blue point here, even in the absence of noise. Right? So you receive this point -2 when both bits transmitted are 0. You receive +2 when both of them are 1. And you receive 0 either when the bit for the first user was 0 and the second user 1, or conversely, the first user transmitted 1 and the second transmitted 0. So this approach definitely fails for the multiple access channel. Right? You cannot, there's ambiguity here, even in the absence of noise, you cannot distinguish the two messages individually, but you can distinguish their linear combination, actually their XOR. Right? Because in this case where you have ambiguity, the XOR of both messages is always 1. Right? So then, in the case of noise, you just make some decision regions here, and you can decode with some probability of error that you can control. This is an uncoded example, but it's a simple illustrative example, and it was a proposal. So this gave the origin to this area of physical linear coding in 2006. So let's see a few more examples. My goal here is to try to give you some intuition about how we will address this problem. So if you understand this example, I think you have enough intuition to understand what will come after that. So let's suppose now we have a 3-PAM constellation. So we want to send 3 symbols that are encoded as -1, 0, and +1. So how should you map this? First of all, how should you map this to bits? Right? Should you just use like 2 bits for each symbol, like 0, 0, 0, 1, and something? I think you would agree that it's more natural. It would work if we actually use integers from this set here, which is at 3. Right? Which is mod 3 from 0, 1, and 2, for instance, to map to our symbol. And the reason is that when we look at the constellation as a receiver, we get these 5 points, right? And at some of them we have ambiguity, but the ambiguity is resolved if we try to compute this linear combination, which is the summation in this set Z3. Okay, so for instance, this point here corresponds either to symbol 0, 0, 1, 2, or 2, 1. Their summation in Z3 is equal to 0. But what if? So let me try to make things a bit harder. So is this fine? This example? So let me suppose now that the channel does the subtraction here. It's not just real addition, but there's a subtraction between the first and the second transmitted symbols. And if you're still trying, so let's keep the same constellation. If you're still trying to compute the same linear combination, which is the summation of the message, then you will see that this ambiguity cannot be resolved. So this doesn't work for this problem, for physical layer coding. So what could you do? Any suggestion? Yes.
Yes. Both transmit transmits 2,
When both transmit 2, one is transmitting -1, and the other is also transmitting -1, but it's negated here, so you get +1 and it goes to 0. So how could you solve this issue now? Any suggestion?
You use the next symbol.
Use the next symbol?
Yeah.
What
I mean, you wait for the next transmission and you call the.
Oh, you just throw this away and wait for the next one?
From a linear system. From the next time instance.
From the next time instance. But suppose you want to do it, so you can do it just in this time instance. W1 minus W2. Okay, so don't try to compute this linear combination. Try to compute something that's closer to what the channel is providing to you. So if we then try to compute W1 minus W2, then it's perfect. You don't have any ambiguity. Okay? Is that clear for everybody? Okay. So this is a simple one-dimensional example. Let's move on to higher constellation. So suppose we have a 4-prong constellation. And the channel, again, just doesn't do anything. And we want to compute the summation. Now this is a vector, right? This is a vector of over F2. Two symbols over F2. And it's easy to see that this is just a Cartesian product of the first example, so you can do the same, and there are no ambiguities here. This is a possible linear combination. But what if the channel now makes this rotation on the second transmitted symbol? So algebraically, it's a multiplication by I, imaginary number. So if you still try to compute the same linear combination, then you get ambiguities that you cannot resolve. So what could you do? So one solution that I didn't put here, but is to reverse the bits of W2. You want to compute, it's not a linear combination, it's a function that is W1 plus W2 reversed. That would work here. But it's not a linear function, right? It's a stranger function. So you don't really want to do that. So it's much easier if we just move on to a different ring. So we go to Z to I. Okay, so the complex integers 1, 2. And try to compute this linear combination. Now I is part of your ring, so you can then attempt to compute this linear combination, and then all the ambiguities are resolved. Okay, and of course this also works for the previous case where the channel is just 1 and 1. Okay, but then we compute this original linear combination. So that fine for everybody? So some observations that we can draw from this example. First of all, the algebraic structure of the message space should not be arbitrarily chosen. Right? It should be compatible with the constellation used. That's one thing we notice. Another thing we notice is that the linear combination coefficients should be chosen to match what the channel is providing to you. And moreover, in general, we may have to use linear combinations over some ring rather than a field. Sometimes we get more structure by using such a ring. In that case, the message space is not a vector space, but rather a module over a ring. If you're not familiar with modules, you can just think of that as a vector space over a ring. That's a good simple simplification. It's a useful simplification if you're looking at this for the first time. Okay, it's much more general than that, but you can just think as a vector space over a ring. So now, some challenges that you encounter. First of all, how do you handle multiple transmitters? We talked about 2 transmitters. We also want reliable communication. We're always doing uncoded modulation, but we want reliable communication. So vanishingly small probability of error, so we have to incorporate channel coding somehow. What if the channel gains are not integers? We only consider integers. And in the case that the channel gains are not integers, how can you optimally choose these linear combination coefficients, which have to be integers? These are some challenges. So let me go to the general model. Now we have L transmitters. The receiver, the relay, is receiving this summation, linear combination of the complex field. We will assume some power constraint on each user. There is Gaussian noise with power n0, and so we define the signal to noise ratio as P over n0. And we'll assume that this vector of channel gains is known to the receiver, but completely unknown to the transmitter. Okay, so it's channel state information just at the receiver. It's an important something here. We don't rely on channel state information at the transmitter. For encoding, we assume that each user has an identical encoder. This could be generalized to different encoders, but let's just do this for simplicity. So a user encodes a message to this vector x of L, and these messages are chosen from a message space that is actually a T module, where T is the community ring with identity. So this ring you can think as the ring from which the coefficients of the linear combinations will be chosen. Okay, so the message space has to be a T module. So you have to be able to multiply elements from the message space by elements from this ring T. We can define the message rate as just the spectral efficiency, right? The log of the cardinality of this message space divided by the number of channel views. For decoding, what does the receiver have to do? It will first of all select coefficient vector A, and it has to be non-zero, and we'll attempt to compute this T linear combination of messages with those coefficients. And if we denote as U hat the linear combination, then it will make an error if U hat is not equal to U. Right, so then our goal is to design a physical linear portfolio scheme with the highest possible rate that allows you to reliably decode this linear combination. So with arbitrarily small probability for various channel gains. And this is our information theoretic goal. Of course, in practice, we also want finite block length and reasonable encoding and decoding complexity. So, just as some preview of what would be a good solution here, it's intuitive to expect that a good PNC scheme will be able to resolve all the ambiguities if there's no noise and the channel gains are integers, right? And when you use the coefficient vector equal to the channel gains, then there should be no ambiguity, just as what we saw before. Moreover, it would be nice if, when you reduce the problem to that of a single user, single transmitter, and the channel gain is just one, then you should be able to get the capacity of the Gaussian channel. That's reasonable to expect from a good solution to this problem. So it turns out that the solution was proposed by Nasser and Gasper. They call it computing forward. And they base their scheme in the use of nested lattice codes with lattice decoding. They extended a scheme by Ares and Zamir, which achieves the capacity of the point-to-point Gaussian channel. And it features that property of no ambiguity when the channel gains are integers. And when the channel gains are not integers, they can achieve a certain so-called computation rate in general. And they also give us a very clear criteria to choose the linear combination coefficients given the channel gains. They deservedly won the CONSOC IT-SOC Joint Paper Award for that contribution. Okay, so let's just look at their theorem here. So basically, for any message rate, and if you use a sufficiently large block length n, and also sufficiently large prime integer p, then you can find a PNC scheme with this message space that can reliably decode a linear combination. Actually, any linear combination with coefficient vector A such that this quantity here is bigger than the message rate. So this quantity is called the computation rate. And you can think of it as like the capacity of some equivalent channel. Okay, so if you, from your received vector, you try to extract some linear combination with coefficients A, this is sort of the number of bits that you can extract about that linear combination from the received vector. Of course, if you can extract more bits than your message rate, then you should be able to reliably decode this, just like your rate being smaller than the capacity. That's the intuition behind. But of course, this depends on the channel gain. question? And then we can see that this gives us a way to find the best coefficient vector based on the channel gain. So we have to minimize this quantity here. And there's actually a shortest vector problem in a smaller lattice.
Shortest is for the large problem.
Sorry?
The shortest is for the large problem.
Yeah, but then the dimension here is very small. It's just a number of users. Right? So it's 2, 3, or 4. So this is doable. And there are good approximations. Okay, so this is an information theoretic result. Okay, it's already quite good because this, in contrast to those previous schemes that I mentioned, this is a reliable scheme. You can make the probability of error as small as you wish. Right? And actually, for many situations, you can show that this is better than decoded forward. So this is a very interesting result. But this is still an information theoretic result, so it's a fundamental limit. How do we actually build practical schemes that can approach that limit? Okay, so we started working on that, and one thing we did was to extend this computing forward framework to allow more general nested lattice pairs with any dimension, and in particular over message spaces that can be modules over a ring. So because basically in their paper they considered just random construction A for constructing good nested lattices, and the field size might have to grow very large. So how can we find more practical schemes that still work under this computing forward framework? We also showed how to find the structure of the message space given any nested lattice partition, and which is useful if you actually want to know what will happen with your linear combinations and decode them later on. Right? So there was also some work by Heron and Ryan on making this practical computing forward using multi-level codes, but they didn't make this clear scheme on lattices. So for now, I'll explain this computing forward framework using this algebraic approach. Okay. The first ingredients that we need are, of course, lattices. So you can probably see the reason for lattices just going back to the first example, right? That's the way we can make this combinations, like summations over the complex numbers, to somehow match to summations over this finite ring. So essentially by using regularly spaced points, we make sure that these different combinations will all fall into exactly the same point. So that's some motivation for regularity here, for structure. So we'll start with a nested lattice pair. So I'll assume you all know what this is about, right? So you have a lattice lambda and a sublattice lambda prime. And let's just recall the main property here of lattices is that any linear combination of lattice points is against the lattice prime. So we have that, but we still need a little more, some more ingredients. So first of all, we need the coefficient ring T So the range from which you take linear combination coefficients of the messages, you need it to be a discrete subring of the complex number. Okay, so you could take just t as being z, the integers, but typically we want them to be complex. So we can represent also rotations. So we typically take this ring as being either zi or z omega, where omega is, these are called the Gaussian integers and these are the Eisenstein integers. So this is rotation by 120 degrees. And then we assume, we require that this nested lattice pair, these lattices are not just lattices, but T lattices. So they have to be close to multiplication by elements from this ring T. Okay, so essentially we are requiring that our lattices are also close to certain rotations. That's all we need. The message space is of course a finite T module. And another ingredient that we need is a labeling of lattice points with points from your message space. So, but the important thing here is that this labeling is linear. So it has to be a homomorphism, actually a surjective T module homomorphism from the lattice, the fine lattice, to your message space. And the kernel of this homomorphism must be your sublattice, your coarse lattice. If you can have that, and also you will need an embedding map. So it's just an injected map that takes messages to lattice points so that you can encode. Okay, but that's easy to get. So if you can get all of the ingredients, then you have physical linear encoding scheme. So let me give some examples to make this more clear why we need these ingredients. So suppose we have this lattice here, so this just extends the whole space. And now how can we label these lattice points with messenger vectors? So this is an example of a labeling of this lattice points. Right? So our message space is this one. So we have 9 messages. And if we use this labeling, then we can see that the labeling is linear. There's a homomorphism. So, for example, if you take, let's say, this lattice point and this lattice point here, and just add the two of them, right? You will get this point, and that corresponds exactly to the summation in this set here, in this space, in this module. And actually, I'm going to space too. Or, for example, if you, let's take 1, 1, and 1, 2, and add them, what do we get? We will get this lattice point. And again, the labeling here, 2, 0, corresponds precisely to this summation of the labelings here. 1 plus 1 gives 2, 1 plus 2 gives 3, not 3, 0. Okay. And the embedding is just a mapping to this region here. And the labeling applies to the whole space. Okay, if we have that, then now we can define this PNC scheme. So encoding is just using the embedding map to take messages from a set of lattice points. And decoding is essentially decoding lattice decoding to the nearest lattice point, and then applying the labeling to figure out your messages. Okay, except that there is a scaling here by alpha. The scaling is a very clever trick that was originally proposed by Erzens and Mir, and then Nazim Gasper extended this trick to this problem. So we see why this alpha is useful. But for now, just think of the the decoding operation as lattice decoding followed by this mapping, this labeling to figure out your messages. Okay, so let me give you an example. Suppose you want to transmit this, so user 1 is transmitting this lattice point, user 2 this lattice point, right, corresponding to some messages W1, W2. And the channel, suppose the channel gains are 2 and 1. So the first lattice point is multiplied by 2, the second is multiplied by 1, and added, right? And here you have the effect of the noise. So you just decode to the nearest lattice point and then read the labeling. The labeling in that case will be 2, 1. One way to figure out the labeling, you can just do mod lambda prime, so move these points to the fundamental region of lambda prime, and so in that case the label is 2, 1, and we can see that it precisely corresponds to this linear combination of the original messages. Any questions so far? So now, what if the channel gains are not integers? So so the strategy here is to multiply the received vector by alpha. So when you do this, you can separate the lattice point and this other contribution, which is called the effective noise. So the point of alpha here is to somehow move these complex coefficients to integers, to make them close to integers, so that you can approximate with these integer coefficients here. Okay? Sorry? Yeah, this is an MMC estimation. So this term here is called the effective noise, and after you do lattice decoding, and then this term becomes unchanged because this is already a lattice point. And then after you do the labeling, you get precisely your desired message. And the remaining term here is your effective noise after decoding on the fine lattice and mapping to a message. So you will get the correct linear combination if and only if this term here is equal to 0. So basically, when your quantized effective noise is in the sublattice. Okay. So that's your expression for the probability of error. And intuitively, we can think of it's useful to consider the power of this effective noise. So it's given by this expression here. This term is related to the mismatch between the channel coefficients and the integer coefficients. And this term is due to Gaussian noise. So by carefully choosing alpha, you can trade between this self noise, this mismatch, and the Gaussian noise. So if you make alpha too large, in order to make a better approximation here with integers, you end up making the Gaussian noise also large. So you have to choose carefully to minimize this power of the effective noise. That's how alpha is optimized to find this expression here, and that's also how you should choose the coefficient A to minimize. Yeah.
So what if instead of multiplying all the coefficients by the same alpha, you use different alphas, like you multiply by a matrix instead of a gain?
You could do that, yeah. You could do that. However, you have to end up with the same A, right? Because you need to extract, you need them to give a linear combination of messages. things. So that's, but yes, you could try to do that. Use multiply your whole vector by different alphas. I don't think this has been studied. Any other questions? So here is how you can find the algebraic structure of your message space. So just suppose you take any lattice, nested set of nested lattice pair. How can you figure out the message space? A message space that is compatible with what you're trying to do. You cannot just take any lattices and use any message spaces that you want. Right? You need some compatibility, and the compatibility is given by actually the first isomorphism theorem. So this quotient of lattices is actually isomorphic to your message space by the first isomorphism theory. So up to isomorphism, there's a unique choice of this message space. If you actually want to see what the structure is, you can use the destruction theorem for modules over a principal ideal domain, and then there's a canonical decomposition of that module as a Cartesian product of this ring, actually. And if you know the nesting matrix of your sublattice into your fine lattice, then you can use the Smith normal form to find an explicit mapping and an explicit, find this explicit decomposition group. Okay, so there's a practical way to find the structure of the message space from any nested lattice pair that you use. Yes?
Do you think that there is really a practical interest in using this? Because, if you use the same lattice, if users use the same lattice, then I guess that just by using some coding construction A or original construction, using codes, it's not useful. Maybe it should be useful when you use different lattices.
Really? So I'm assuming here that all users use the same lattice.
Okay.
All users use the same. So our motivation to study this is that we didn't want to use construction A.
Okay.
Okay, they just assume construction A with a large P, and then you get this message space. So it's not hard to get this message space. But what if we want to use other lattice constructions, such as construction D?
Yeah.
You end up getting something strange like this. So I'll show you.
Okay.
In a second. Okay, so that's exactly what I was going to talk about. So constructions of lattices from code. So there are many constructions. I'll focus only on this one. So construction A, complex construction A, and construction D. And a big advantage of these constructions is that you can think of them as coded modulation. So you separate a decoder, you separate coding and modulation. So it's not like a decoder, but at least a decoder. And then you can use codes to construct lattices. So for construction A, what you need is a linear code over ZP. Okay, so just take a prime P and construct a code over ZP. And then the lattice is defined as the embedding of that code into the integers plus all the multiples of P. And then you get a lattice. If you want, this is a real lattice, right? If you want a complex one, you can lift this lattice to the complex space. So you just use the same lattice in the imaginary part. When you do this, you get a ZI lattice. Okay, this lattice is closed under multiplication by I. So that's an important property here. And then the sublattice is just the multiples of P. Integer vectors. And then you get that structure of the message space. Okay, that I'm a P K copy of that. And this is a finite field in some cases. So then it will be vector space. And we can then study some properties and probability of error for such lattices. And it's interesting that you can find. Can you hear me?
Yes.
The error probability properties of such a lattices can be mapped to some properties of the underlying code. And in particular, if you take p equal to 2, then this parameter that you need is exactly the minimum Hamming distance of the code. So this will give you the performance of the scheme for IS will be driven by this scheme. Okay. So that's a simple message space. And then you can, in practice, you can just view your construction as this coded modulation. So you have an encoder, and then a modulator is just a p-PAM modulator. Okay. But you're doing separately the real and imaginary parts. So in the end, you get a p-squared constellation. And interestingly, the decoder can also separate. So after scaling, it can separate real and imaginary parts of the received vector and do the decoding on each linear code to extract the real and imaginary parts of your message. So that's something easy to implement, especially if you take p equal to 2, you're just using binary linear codes. For which there is a lot of you can also use complex construction A. So in this case, we are generalizing the ring here to, it's T. So it could be, for instance, Z omega, the set of Eisenstein integers, and the pi must be a prime in that ring. So in that case, if you have a linear code over this, actually this will be a field, and then you can again define using the same expression. You can define complex construction A. Now the lattice is already a T lattice, so it's already close to multiplication by elements of T. And this is quite interesting when you take T to be the set of Eisenstein integers, because then you can get other modulation schemes based on the Eisenstein integers. So I don't have a picture, but it's like you're using this modulation here. Or just the hexagonal lattice. Right, so for instance, if you take if you use this prime over in the set of Eisenstein integers, then your field is isomorphic to F7, and you're using that modulation there with 7 points. So Naranayan and others use those Eisenstein integers to be quite interesting PNC schemes. Okay, and if pi is equal to 2, you get F4. But in my opinion, perhaps the most interesting construction is construction D, because it generalizes construction A, and it has very interesting properties. So construction D is based on nested linear codes that are given by some generators here. So G1 to GKI are generators for the code CI, and they have to be nested, so one code is a subset of the other. And then you construct the generator matrix of your lattice in this way. Okay, so you just take the embedding of these generators. So these are the rows of the generator matrix of the linear code. So you just take, so the first K0 generators, you embed them into Z. Just take the integers. And they are unchanged. Okay, the first K0 for the code C0. And then the next K1 minus K0 generators, you will multiply them by P. And then the next K2 minus K1 generators that together will generate code C2. You multiply them by P squared and so on. Okay, so that's a possible description of construction D to get the generator matrix of the ladder. And this generalized construction A, when you just have one code, and you can again lift it to lattice over Zi, just by using the same lattice on real and imaginary parts. And now the message space gets this structure. So this is not trivial to get this structure. Just to give you an example, so this is a module, right? It's not a vector space or this is a much more general structure. So just to give you an example, if you use two codes, two nested linear codes, with dimensions 20 and 8, for instance, and if you take P equal to 2, and then this is the message space that you get. So you have 20 coefficients in this ring, Z for I, and 60 coefficients in this ring, Z2I. And then you're taking linear combinations of messages over in this space. Okay? And then you will have to, the coefficients will have to be in Zi. But the messages are in this space. So it's interesting to observe that construction D is equivalent to coded plumb modulation with a constellation of size P to the 2 times S. So if you take P equal to 2, this is just, you can view 4 plumb, 16 plumb, and 64 plumb constellations. But the coding uses multi-level coding. You can, again, due to the lifting, you can decode, you can process real and imaginary parts of the data separately. And you can decode in a multi-stage fashion. You first decode C0, the code with the lowest rate, and then subtract and then decode C1 and so on. Okay, so you can do the decoding. If P equals 2, encoding and decoding is just performed over binary linear codes, which is something very well studied. And but by doing that, you can achieve large, high spectral efficiency, okay, that you wouldn't be able to do with construction A and P equals 2. So we can get the best of both worlds. We can get high spectral efficiency and still use binary codes. Okay, but just one important point to make here is that why is this at all different from just using lattices for a point-to-point channel? Okay, the whole difference lies in the fact that we need to consider the structure of the message space. Okay, because then, so there are lots of papers, let's say, on lattices with construction D for a point-to-point channel, but nobody really cares about the message space. These are just bits, right? As long as you transport bits from a transmitter to a receiver, you are fine, right? But this is for a point-to-point channel. When you have this multiple access channel, then that later on you want to relay that message to other users, then you have to pay attention to the structure of the message space, because you will take linear combinations of messages. That's important thing here. So we have to worry about the structure of the message space. And I just want to mention that if you can get this working, then you can extend the scheme to larger networks. You don't have to be limited to the two-way relay channel. So let's just suppose a much larger network with L transmitters. They all each take a message from this message space, and they transmit, and then let's say this relay will get some interference, right, between all those transmissions, and then decode to a linear combination over this message space, which now may be a module. Right? But once they do this, they can then again forward that linear combination to other users, and so on and so forth, until this transmissions reach a destination. Destination will compute a linear combination of the transmitted messages, right? Which are linear combinations of the original messages. So, linear combinations, you can in the end make up a matrix, just like we were discussing yesterday. So, linear network coding. We have this original packets, messages, some transfer matrix, and then here the matrix observed at the destination, and then you can just decode by solving this linear system. Okay?
But in this case, the chances of having an inverted matrix A are much smaller than if you use finite fields.
That's true. The chances. So if you can use a finite field with a large cardinality, sure, you will get the matrix will be non-singular with higher probability. So
is there any such results for finite fields?
there are. So exactly we have a paper on that. So the difficulty here is how do you actually do network coding over these rings, right? If you want to use construction D. So there's a way to do that. So how do you solve a linear system, for instance, over rings? Right? So there are ways to do that. So we have studied how, what kind of capacity you would have from a channel with a random matrix over some rings. And definitely there is some loss if you use P equal to rather than a larger field. On the other hand, there's a trade-off, right? Because if you use P equal to, then you can use binary codes. You can use LDPC code and so on. How do you do that with P equal 7 or P equal much larger? So there's a trade-off on that. Any other questions? So, just to finish up, I just want to mention that this is just an introduction to the problem. There are several other questions that can be asked. How do you efficiently find the best A's? Okay, so it's the shortest vector problem, a very specific one. Maybe there are ways to do the search more efficiently. What if you don't have channel state information at the receiver? Can you still decode? What can you say about the computation rates when you use Eisenstein integers? So these authors could find some previous work where they could also give computation rates for the case of Eisenstein integers. And in some cases, it turns out to be better than using Gaussian integers. And you can, these authors here have proposed new lattice constructions from codes that are compatible with computing forward. You can also study how to build practical nested lattice codes, constructions and decoding algorithms. So this is also an important problem here. And there are many other problems about, let's say, asynchronous. How do you deal with asynchronous communication, communication over channels with inter-symbol interference, and so on. So essentially, any problem that you can have for a point-to-point channel, you also have here, but it's just harder. Okay? So there's a lot that can be done in this area. So I'll stop here to compile a list of reference if you're interested. Okay, and that's it. Any other questions?
If you have CSI transfer, then you do something better.
Yes, it will be much better. So here we're really assuming that you don't have CSI at the transmitter. And the one reason is that how can you tell the transmitter, right, what the channels are? When you have such multiple transmitters in this such a scheme, imagine they're all transmitting at the same time, you're not really estimating each channel individually. So it becomes hard to find, to get the CSI at the transmitter in the scheme. So that's an assumption that we use in this approach. So that is trying to be more practical. But definitely, if you have CSI at the transmitter,